science like there's no tomorrow.
Welcome everyone after the break. Today is block number 3 of lecture number 6 on building of a yield curve. In the previous lecture, we discussed the concept of a building of a single curve. Today, we will go into more practical aspect where we talk about multi-curves and the relation of multi-curves and default probabilities of counterparties. So this is very insightful, very important block where, as before, it will be very practical because we'll be also having Python implementation of multi-curve. And today we also have a homework assignment. This homework assignment will require some Python coding where we have to extend existing codes, the codes that I provided, with additional, let's say, instruments of the calibration of a curve and also looking at some hedging aspects. I hope you enjoy it. Concept of multi-curves is rather fresh, rather new in financial mathematics. It was developed after financial crisis in 2008, 2009, and since then is present until today in the market. Until now, or until 2008, if somebody was building a yield curve was insensitive to potential default probabilities of a counterparty. By applying multi-curves, we can include extra information regarding the frequency of the payments and the associated risks of default. To give you an example, if you have a contract with a counterparty and you lend your money for a month, or you have a counterparty that you lend your money for 3 months, you may think, okay, the one for 3 months could be more risky than the one for a month, because there is more time that the counterparty can default. And this is the concept, this is the problem that multi-curves try to address. So let's take a look at the definition of a multi-curves, where exactly it comes from, and what kind of financial instruments we can take a look at to really see this multi-curve arising. So let us consider a tenor structure, actually 2 tenor structures. So we have some interval ti minus 1 and ti plus 1, and we consider 2 tenors. So first tenor, it goes from ti and ti, so ti minus 1 to ti. So if we have interval here will be ti minus 1, here we have a ti, and second is ti plus 1. So the first tenor is this period, and then we have a second tenor, which says it's actually ti minus 2, and this will be tenor much wider. See, so it's about the frequency. So first tenor, it's twice as fast as the other one, and that's actually, this is the type of instruments we will be looking at to exploit the concept of spreads between different type of curves. In practice, we consider those kind of, let's say, multi-curves. If we see a difference between the frequency of the curves, let's say 3 months or 6 month curves, those would be the typical that we will see that there is a difference in discount factors in building also of those curves. So, okay, so we have 2 tenors. One is a high frequency, you can say 3 months, and then one is of lower frequency, in this case, let's say 6 months. Okay, so we have 2 different structures to price a derivative. From the financial, let's say, from the financial arbitrary perspective, it doesn't really matter if we have a LIBOR rate over this period or bond, and we reinvest this bond until this moment. Essentially, that would mean that it's exactly the same as the financing over the whole period. So whether so this is the same as you can think of a money savings account. If you put your money and then you reinvest after a certain period of time, it should be equivalent if you have invested for a longer period of time. Of course, now we exclude the element of a curve and different types of yield curves, but basically the idea is that the frequency of refinancing is faster or slower. So this is how we can illustrate. We have 2 periods of time, and we have a ti minus 1 with ti and ti plus 1, and here we have exactly the same periods, but now we have a LIBOR rate over the whole period of from ti minus 1 until ti plus 1. So like I just mentioned, the strategy based on the arbitrage arguments, the strategy involving reinvestment should give exactly the same result as one investment over the whole period. And this is what what it illustrates. This picture, first one, you can consider as a 3-month curve, for example, where we have LIBORs with a frequency of, let's say, float frequency of 3 months, and then here we have 6 months. So this is, for example, 2 different curves we have. Okay, so now what we can also do is to look at the so-called basis swap, because in this case, what we have, that we can actually construct a contract. So we can do is that from this financing strategy, because we have recompounding here from ti minus 1 until time ti, and then ti to plus ti plus 1, and this should be equivalent with this period. So what we can do, we can define a contract. You can see we are summing over all those. This is high frequency LIBORs minus the whole lifetime of a swap with a lower frequency. And then we know that arbitrage-free condition should apply, that this should be 0. However, in practice, this is not. This could vary depending, of course, on the type of a curve we have and also the frequency of the payments. And this is associated with the fact that if you are lending your money over 3-month periods, you would expect that probability that the counterparty will not pay you back is lower if you lend your money for 6-month period. And this is essentially what this contract would show us. So this would be this non-zero. Thus, the difference, if we see any difference in evaluation, so if this difference of these two swaps is not 0, that's called basis swap. So that's the term related to subtracting of looking at the float rate swaps. So we don't, you see, there's no fixed rate. We have looking only at the float side. And if there is a difference in the payments, between those, let's say, a reinvestment, that's called basis between different LIBORs. We can illustrate this, we can show it, look at here. So for this basis swap, so it's a contract where we exchange float contracts with 2 legs, both are float. So it's called floating for floating basis swap, where we exchange, for example, 3 months payments over 12-month periods. So we have in the year, for example, we will have, in this case, we have 3 for 6, but we could have, for example, 4 times a year, 3 months, every 3 months we will have a float payment, and we have also 1 times a year we have a 12-month payment. And that will be basis floating for floating, 3 versus 12, or for example 3 versus 6. And of course the combination between the two, so it's a 3, 6, 3, 12, those will be different basis swaps, and also those will show you exactly how what are the relations between different curves. Because each frequency, like we have here, or it's a 1-year frequency, or 6 months here, and we have 3 months here, each of those frequencies will correspond to different curves. So this was important to keep in mind. Each individual frequency determines the curve. So if we have 1 month frequency, that will be 1 month curve. If 3 month frequency, 3 month curve, and so on. So this is the most important takeaway. So the frequency of the payments will determine how many basis swaps, how many different frequencies we have, and also the type of a curve, and of course what can happen, those curves could also have different configurations regarding the interpolations and so on. So there are a few important takeaways regarding yield curves and the motivation of having them. The first is that from the risk management perspective, it is safer to receive frequent payments as the counterparty may default between payments. So in a case when we have a very frequent payments, there's less money to be lost. So this is important, I would say the most important motivation for multicurves. Until the financial crisis, 2007, 8, and 9, that was, let's say, there's a whole period when we had a crisis, the basis spread, so if you look at these contracts that we just defined, those were really negligible. So there was really arbitrage-free, nobody considered that the frequency of payments may have any role. And after the crisis, this has diverged. So we could see basis spreads between different tenors. And those tenors and those basis spreads were not anymore negligible. There were multiple basis points difference between different frequency of the curves. These days, interest rate instruments with different tenors are characterized by liquidity and a risk premium. So this is how you should think. So the main difference, so this spread between 3 months and 6 month curve, it's considered to be a credit risk premium. So this is the same what we have seen before once we talked about the yield curve issued or yield curve based on market instruments and also yield curve based on bonds issued by a company. That the spread between the two would indicate about a risk premium. And this is the same what we have in curves itself. For the mortgage crisis, so again, this is 2007, 2009, discounting was based on a single curve. So this is or pricing was not only discounting, because this was, maybe this is misleading. Discounting and pricing was based on a single curve, which was used for all the tenors. So we had only one curve, and this curve was used all over the place. So what we have learned in a previous block about construction of a yield curve and interpolation, that was always the case until the financial crisis. Since the financial crisis, this pricing is more involved because we need to take into account that there are additional, let's say, risk premia between different tenor structures. And in this block, we will concentrate on we will build in Python a curve package, let's call it. So multi-curve, so curves where we have different tenors, we calibrate them, and also we calibrate a discount curve used for valuations. But before we get to the Python coding, it's important to understand what is the machinery to construct those curves. Maybe one more point here. The existence of non-zero basis spread in the market after the mortgage crisis essentially implies that when modeling interest rates forwards, we need to distinguish between different tenors. So if you see a swap with a 3-month tenor or 6-month tenor, it should be also for you a red flag that you should not take one curve for both swaps, but those swaps should be priced with a different curve, different yield curves. And this is illustration. This is a real illustration taken from the market, where I was plotting. This is the instantaneous forward rate, but you can consider as a yield, where we see that this is the lowest one is the high frequency, so it's a daily rate, so it's a tenor of 1 day. Then we had the black one, which is a bit higher. You see it's 3 months. Then with 6 months and 12 months. So the higher the tenor, so higher the rate, because there's more risk involved. So it's a risk premium. Basically, it's actually expressed here. This is the spread between different curves. Here we show everything goes against 1 day curve. So you can see higher the tenor, larger the spread between curve and the 1 day curve. It's also illustrated actually here. So this is basically, you can see that here, this is the 12-month difference. So we have around 25 basis points that you have to pay extra for this risk that is associated, that your counterparty may default in between, or there is this risk premium included in the price of those swaps, for example. Since we already have argued about the reasons behind the construction of multi-curves, the 4 curves for different tenor structures, we still have to agree about discounting, because as you can imagine, we still in every future cash flow. So even if we have a cash flow which is based on, let's say, 6-month, 3-month, 9-month, 12-month tenor, we still have to discount those future tenors. And the market consensus is that the discounting should take place based on highest frequency tenors. So this means that the least probability of default. That would be a proxy for the risk-free discounting. So typically, for discounting of multiple curves, we use unique curve, which is associated with a tenor of, let's say, 1 day. Typically, this is the shortest tenor available. So this is what we have here. So we have unique discount curve, which is typically 1 day tenor. And here, what we have here, so we have multiple tenors. We already established that. We have tenors of 1 month, 3 months, 6 months, 12 months, even could be up to years. Possible and optimal choice for discounting is a curve which carries the least possible credit risk. So the risk premium should be the lowest. And of course, that suggests that the discounting curve should correspond to the curve with 1 day. And in Eurozone, this is called IONIA, the Euro Overnight Index Average Curve. And in the US, it is the Fed Fund, so thus a US Federal Reserve Overnight Rate. We also have to keep in mind that under multiple curve framework, well know the arbitrage-free, the single curve assumptions, they don't hold. And like I already mentioned before, if you see a swap, or if you are asked to price a swap, let's say with 3 or 6 month frequency, then it should be also indicated for you which curve you should use to price that particular swap. And that's quite important. In this section, we will link this, let's say, market observations about including additional risks into pricing, and we will develop a framework for pricing of those derivatives. As you can imagine, that the, let's say, practitioners, so the market reacted first. So once the crisis happened, we have observed the increase in the basis spreads between different tenors, and only then, let's say, the theory was developed to support market behavior. And of course, it was in the opposite, where we, when a theory was first developed and then market followed, it was opposite. So market behaved in a certain way, and practitioners and also the analysts try to understand what exactly happens. And today I will illustrate the mechanics behind inclusion of default probabilities in the building of those multi-curves. Okay, so if we have an expectation of a LIBOR rate, and we have, this is what we have seen already before, once we talk about measured transformations, I have introduced 2 indices. So we have a discounting, DC, so discount curve, and we also have a FC, so it's a forward curve. Forward curve, you can think of a curve associated with a tenor, which is not 1 day, because 1 day we will use for discounting. So we have 3 months, 6 months, and so on. So if you apply this measure change transformation that we already have seen before, then naturally we will have a zero coupon bond from the forward curve, and then we have corresponding forward TI forward measure for the corresponding line. And of course, we just mentioned that discounting in the world of multi-curves, it's agreed that discounting should take place based on the least probability of default, or curve with the least probability of default. This means that we should discount with a 1 day curve, not with the forward curve. And you see that this is basically inconsistent here. So what we have to do, we have to change the definition of a LIBOR. In order to handle this properly, we will need to change the LIBOR such that the LIBOR rate, it is based on a discount curve, let's say the risk-free curve, and also includes probabilities of default of the counterparty over a period of time. This period of time will be determined naturally by the tenor structure. So in other words, the measure change technology we have seen already in the previous lectures for changing measures from the spot to forward does not comply with the separation of discounting and forwarding curves. Extended versions of the LIBOR rate and measure changes are necessary to address this issue. Okay, so how to include this probability of default in our multi-curve framework? We have to do it by inclusion of a concept of default probability. We already have seen similar graph in the beginning of the previous lecture, once we were talking about the forward rate agreements, when 2 counterparties exchange cash flows. It was the basic contracts we have seen. So here we have the same. So we have a payment which will take place at time t1, and we have a second payment which will take place at time t2. So we will lend €1 to counterparty, but only, so we have a minus €1, but only if this counterparty will default after time t1. So this means that, maybe it sounds silly, but this indicates that counterparty should exist still at time t1. Of course, if this counterparty doesn't exist, we would not even make this first transfer to the counterparty. So this is basically the way how we say we only give you money. Of course, first of all, if we want to give you money, but suppose you're our counterparty, we would like to have a transaction, but we only do it if you still exist. And on the second hand, we will also receive money from you, but we will receive money that we have invested, we have lended to you. So it's a €1 back, but only if you have also, let's say, defaulted after time t2, or you are still, you can also say you are still alive, or you were not defaulted before time t2. So we can receive only if you haven't defaulted. Of course, if the counterparty had the default, then we won't receive anything after time t1. We just lose the money that we have lent. So here we receive only if the default will happen afterwards, because then we actually, from this perspective, we don't really care because we receive the money back. And also we have this rate over the whole period of time. So we have this €1 and we have this K, which is the rate of this €1 multiplied by amount of time that we have lent this €1. And only we also receive this premium, let's say, only if the counterparty defaulted after time t2. So if this party didn't default at time t2, we will receive this money. So that's basically the concept. You see, it's a very simple extension of what we have defined before. And here, TDB, this is the random variable you can think of. It's a random variable indicating the risk of default of time. So this is kind of probability of default. Actually, this is, to be more precise, TDB, so time, this is the T indicates time, is a random variable indicating the first time probability of default. Of course, typically if you have a first time, you also have the last time. So it's first is the most important because after the default, there's nothing can happen. And so you have a distribution indicating in time how likely counterparty is to default. This probability of default typically will be extracted from market instruments. So if a counterparty issues bonds or CDSs, there's credit default swaps, so credit derivatives. From those, it is possible to estimate the probability of default. In a case when, for example, a counterparty, we cannot really extract from market information probability of default, then typically what banks do, or financial institutions in general, what they do, they try to associate the company with an industry risk. So for example, it could be that the railroad industry has a different probability of default than production of car, and so on. So then in this way, you can kind of classify, given the specification of a company, given some, let's say, 20 different questions you can ask a company, and given those 20 different questions, you can assign probability distribution of a default at given time. So this is basically how this works. Of course, it is often very subjective because it's not really implied from market instruments. But if you don't have market instruments, you have to still associate those risks somehow. Okay, so this is basically what we have defined. Of course, now what we have to do, the next step, would be to price this derivative, including probability of default. So what we do what we always do, we discount all the future cash flows, and we take expectation. So the first cash flow is from time t1. What we have to also do, we have to assume some independence here, because it's important you see these expectations of money savings account. This interest rate in money savings account is stochastic with probability of default. We have to assume that probability of default of a counterparty will be independent of interest rates. This is necessary condition if you want to derive it. Otherwise, we need to think of some kind of copula or a different type of, or even maybe solve it analytically, but it will be rather involved to join those two distributions. Okay, so we have discounting from the first cash flow, so it's -1 we discount today, and this is what we receive. So this is what we pay to a counterparty. This is what we receive back. We receive back €1, and then interest rate from over the period of time. And again, this is from time t2, so we discount with the money savings account t2, and only if the default didn't happen before time t2. So it has to be after. Okay, and the first expectation, assuming that there is independence between interest rates and probability of default, we have a discount factor, the zero coupon bond, and then we have this expectation and indicator function of a probability of default bigger than 1. For the second part, we have something similar. So we have this, again, a payoff discounted using the discount factor, and then we have probability the default will be after time t2. We know the property that if there's an expectation, we have indicator, This is the same as we would have probability that event will happen after the default will happen after time ti. And this is it is because it's cumulative distribution function will be with a less sign here, right? Less or equal. So here we have a survival probability, so-called. So what is the probability that party will be still alive at time ti? And this is often associated with a hazard rate, which is defined as the e and the minus integral of ti, and there is a hazard function. So this is the convention how we typically associate probabilities of default and hazard rates. And this hazard rate can be estimated using credit default swaps, so-called CDXs, which are the credit derivatives, which essentially the contracts that one counterparty pays some amount, and from the other party it only gets a payment if a default of a counterparty would take place. So from those kind of contracts, you can receive, you can imply what is the probability of risk. So if you are paying for insurance, higher the premium you pay for your insurance, then it's this will have impact on your estimation of how likely you are to default. And this is how the convention is. So we have market quotes. From those quotes, you can calculate those risk premia, and this also indicates what is the likelihood of your default. Okay. So next step. So once we have those, if we substitute this, if we use those indicator functions, we just define them as d. So this will be this integral over minus hazard rate. We can formulate it as follows. So we have this value of this derivative. It's not necessarily option value, it's just derivative. Of course, option you can think of because we have this indicator function, so that to some extent it is considered to be an option. And we have discounting, and then this is with those d's which correspond to the default. And what we have done before, once we were evaluating swaps and other derivatives, we were always looking for, okay, at what strike value this contract would be equal to 0. Because that's typically how you would enter those kind of interest rate contracts. So if you set this to 0, you can find that we have a strike, the fixed rate, for which this contract is equal to 0, and this is 1 over accruing period. And then here we have those discount factors. So those will be used from discounting curve multiplied with a correction, let's say a risk adjustment. So those are the dt0, t1. As in the single curve setting, a first strike value at which two counterparties agree to exchange funds is called LIBOR rate. So you see this resembles exactly what we had before for the LIBOR rate. Of course, now we have a slightly different definition, because now our LIBOR depends on this credit worthiness. So this D, because we include this probability of default, this D has to be included, is included in LIBOR. So this is not the same LIBOR we have seen before, because that one was risk-free in terms of there was no probability of default inclusion. Now we include this, so now we have a different type of LIBOR. So you can call it a risky LIBOR. But as you see, that's basically very much resembles what we had before, except for the zero coupon bonds. They have to be adjusted with this correction terms, the risk adjustments. And how it happens in practice? In practice, once we deal with zero coupon bonds, so when we were constructing the yield curve, we have those zero coupon bonds, and we also had this kind of convention. It was R times T, right? We were looking for those spine points. And market convention also is to do the same for those risk adjustments, to also define in the same way. You can also do E minus HI, for example, TI. So you say it's equivalent, and this will be the mapping of this hazard rate function. So this one, you can still map it to some kind of effective HI. So practitioners often associate this hazard rate, so the one that we have just seen, in the definition dt0 ti as a spread between risk-free and the unsecured rate of different tenors. So this is what we have established. So this t0 ti can be interpreted as a discount factor, because this is typically how people like to operate. Once you have a discount factor, you can also think the immediately of a curve, because this is how we have done it. The yield curve essentially is a collection of zero coupon bonds, discount factors. So if we can, let's say, formulate the default probabilities, we can link the discount curve with the probabilities of default. This also means, okay, we can essentially build another curve on the top of the discount curve, and that will be our curve corresponding to a particular tenor. So, okay, so we see that in order to determine a fair price of unsecured LIBOR, so the one that the counterparty would default, this is indicated by this L hat, a secured risk-free curve is needed from which the zero coupon bond should be computed. So first we compute the risk-free zero coupon bond. So this will be done on this, let's say, daily tenor structure. And then we add this additional zero coupon bond to represent additional risk premium that has to be added. And of course, we have to keep in mind that we have this a tau, because this will be for every different tenor. For every tenor, we will have a different curve, essentially. So this means that we every risky tenor, so it's a p tau I, we have a risk-free one. So this one is unique for all the tenors. This will be a discount curve that is used for all the tenors. And then we have this adjustment which corresponds to particular tenor structure. So you see it's very, very much alike what we have seen for single curve, except that we have a single curve and then we have to correct it, multiply it with this additional, let's say, zero coupon bond, essentially. Okay, so the LIBOR, the risky LIBOR, so the new definition of a LIBOR now, because now we have substituted this P tau I, we have a risk-free zero coupon bond and also this risk adjustment that we have. So this is the new LIBOR definition. And then, of course, the objective would be to construct this LIBOR the curve corresponding to the particular tenor using discount curve and also market quotes. So that basically, this will be our objective in a Python simulation. Okay, and maybe one more comment here. When a risky LIBOR rate is determined, it is important to discount the future cash flows that depend on this LIBOR rate. And then this means that we will discount, the discounting will be based on a risk-free rate, and the forecasting part will be done on this risky line. So of course, now we have to go back and say, okay, suppose we already have established what is the discount curve and how it is related to the particular tenor. We are at the end interested in pricing of derivatives like swaps. So after the crisis, the consensus has been made that the best approximation for the risk-free rate is the overnight rate. So this is what we already have established. The contractual agreement of an overnight index swap are that a counterparty pays a fixed rate and receive a daily compounded overnight rate. So this is more specification how this one-day curve, what is behind this curve, that we have this daily compounded overnight rate. So that's all associated with risk-free rate. Okay, so now by combining the concepts of risky LIBOR and the rate of OIS, this overnight swap, the pricing of a basic instrument, like interest rates or like interest rate swaps, can be done in the following way. So we have a summation, so this part corresponds to the payer or receiver. We have notional, we have a discounting, so it's a sum over all these future cash flows. We have a discounting, this is risk-free, and then we have to calculate the expectation of this forward LIBOR under that corresponding TK measure. This is, of course, a little bit problematic because TK measure may not correspond to the risky bond, so then we have to do some approximation. But this is basically the essence what we see here. So we have discounting, and then we have to do some expectation of this LIBOR under a particular tenor. So this expectation, how it is computed, it is essentially approximated by this risky LIBOR as we see today. However, it's not completely correct, because this is different martingale measure as we would have under the T-forward measure, which is risk-free. So this is what you can consider as some kind of approximation that is accepted by the market. So under that condition, the value of a swap is simply so this expectation is actually gone. We see only the cash flows corresponding to the zero coupon bond, so discounting of the under the risk-free rate, and then we have a difference of a LIBOR rate minus fixed rate. And this LIBOR rate here, it is estimated from the tenor, from the new curve, which is built on the top of this discount curve. And this new curve includes this risk probabilities of default. This is additional, this risk premium spreads. Okay, and maybe one more thing to mention is that this construction that we have just discussed when we have a discount curve and we just build those tenors, it is not straightforward so much, because in practice, those markets are not so much, those tenors and those instruments in the market, they are not so much separable. We cannot really say those are the 1 month instruments, those are 3 month instruments, and you can build those curves on the top of each other independently. There is some kind of so-called circular dependency. And this is how it goes. So because of the some market instruments, like for example, Ionia, are insufficiently liquid for some maturity. So if you have this Ionia instruments, there can be less liquid after 1 year. However, what is liquid are the basis swaps instruments. So if you look at the market, you would just try to bootstrap a discount curve from the market. However, only the part, the up to 1 year part is liquid, you can really use it. But for the later maturities, you don't have really good instruments. However, market prices some other instruments, which are the basis spread instruments. So you see, if you like to use your discount curve, but at the same time, you need to bootstrap the discount curve, but you don't have this bootstrap curve, but because there is a spread. So this also means that there is some kind of interdependence between 3-month curve and discount curve, because they are not separated in the market quotes. So this means that essentially 3-month curve would depend on a discount curve because it's built on the top. On the other hand, discount curve is dependent on 3-month curve because we have spreads in the present in the market. So there is an interdependence between all those curves. And essentially, if you like to really address this problem correctly, you need to calibrate all of those curves with taking all these basis spreads into account. You need to calibrate them at once. That's, of course, a much more involved task as what we have done so far, at least what we have described so far. Because right now, in our scenario, we build curve by curve. So we have a discount curve, then we build 3-month curve, where the input is the discount curve. And then we use those additional quotes from the market for 3-month curve. And then we do 6-month curve, which we based on 3-month curve and discount curve. And then this is the way how we can build it up, depending, of course, on what we have available in the market. However, if we really want to, let's say in the practice, this won't be so easy because there are some spread instruments involved, which require that you have to calibrate those things at once. However, the extension, let's say the circular part, I'm not going to discuss further in this course on how to implement that. I will give you the description. We will dive into the coding on how to do it in a case where we have this kind of separation. So we can build discount curve, then we can use this discount curve to build 3-month curve, 3-month curve to 6 months, and so on. This is our today's code. However, please keep in mind that this is very important. The circle of dependency is also very important. On the other hand, if you think, okay, so if you don't do circular dependency, you will do it wrongly, right? Because this is what natural conclusion would be. However, maybe not necessary. Maybe you are just having, let's say, inconsistency, but you may be consistent in being inconsistent. What that means is that if you have used your curves, you have calibrated, let's say, like we just discussed, 1 by 1, and you're able to price all the market instruments, then in essence, you can consider yourself to be fine. Because at the end, you priced everything back to market. So where you will see inconsistency is maybe in hedging instruments, because this means that instead of buying on some particular spread or 3-month instruments or so, you may be, according to this, let's say, construction, there'll be more risks in the place that it should not be. But overall, you are consistent within your assumptions. So for example, if you have to give you maybe a perspective of Black-Scholes model once we talk about pricing, even if you have an interest rate in your Black-Scholes model incorrectly chosen, you may still be able to exactly match the market quote, because this inconsistency of taking wrong interest rate will be encapsulated in sigma that you would use to calibrate the model. Therefore, as long you are not hedging your interest rate risks, you are kind of consistent in hedging your other risks like vega and delta, etc. So this is some kind of parallel, let's say, relation between implied volatilities and multi-curves and the circular dependency. However, ideally, you would like to use the circular dependency, but there will be a minus, of course, that computationally, these Jacobians that we have built, they will be significantly larger. This is basically the cost that you have to consider. Now we will see how to implement multi-curves in Python. In this experiment, we will rely on previous code that we have developed for pricing or construction of a single yield curve, and we will extend that code to handle also multi-curves. How we will do it? First, if we remember from the previous slide, the pricing of swaps, it's here. Pricing of swaps requires that we need to have not only discount curve that we had before, but also we need to include additional argument forecasting curve, let's say curve corresponding to the particular tenor. Also, other thing that we notice is that maybe you remember in swaps derivations, because those zero coupon bonds in the LIBOR were the same, let's say under the same curve as the discounting, many things could simplify and we could use harmonic sums in order to simplify the expression with a really nice closed form solution for that. In this case, of course, this separation between discounting and forecasting is not really possible. Therefore, we have to adjust our definition of interest rate swap, let's say our code for that. We need to incorporate two curves. So we have two curves as the input, and we need to use this new technology also to calibrate new yield curve given that the data. So this is this experiment. In the experiment, the curve building will be made sequentially. So first we build a yield curve, the discount curve, and then we use this the discount curve in order to bootstrap the new curve, the corresponding tenor, using also market quotes. Okay, let's take a look into quotes. So first, we start with an extension of a swap definition. So we have a new IR swap multi-curve, and we have one input is for the zero coupon bond, for the yield curve, let's say, for discounting, and other one is for forecasting. Let's say the one corresponding to the frequency, so it's corresponding to this n frequency of a swap. And here you see that what we do, we define LIBOR forward rate, which is based on this new yield curve. And then we do, in the swap calculations, we do discounting using the discount curve. And then we multiply with a LIBOR minus stripe. So this is essentially what we have to do to handle pricing of a swap in a multi-curve setting. So it's rather straightforward. And then in the main code, first part, of course, is that we still have the same initial conditions for initial guess for calculation of spine points. We have linear interpolation. We have market instruments. We assume here that those are market instruments for a discount curve. We still have 8 different swaps to bootstrap to construct our discount curve. Here we calibrate, as we just did before, our discounting curve. And here we construct this curve. So we have initial and we have the bootstrapped curve that we are going to use for pricing. So here, this is basically what we have done it already for previously, where we compare, look at this spine points value of a swap before the construction of a curve and after the construction of the curve. This is some kind of sanity check whether our algorithm worked. Okay, and this is the multi-curve setting. So what we do first, we perform some kind of a sanity check. This means that we will essentially, in the first step, we will check whether our new interest rate swap gives the same value as the single curve swap. What we can do here, we can actually substitute. So I'm defining the forward curve, the tenor curve, as to be a deep copy of the discount curve. And then obviously, because those two curves will be the same, then essentially if swap and swap 1 MC, those should give me exactly the same value. So this is what we will check here. So this is a sanity check whether the implementation of a new swap it's still consistent with a single curve setting. So just basically use 2 times the same curve, and then it should be equivalent. This sanity check is because we have implemented new swap, which is slightly different than previous, and that's a natural practice that we will check whether still the setting collapses to the single curve setting. In a case, for example, where the basis swaps will be equal to 0, so there will be no spreads, no risk premiums, then the technology that we have here, the new algorithms, should still collapse to the old approach with a single case. So that's something to keep in mind. Okay, so now what we do, we define 4 swaps. So those are the swaps corresponding to our new curve. Let's call this curve, let's say, 3-month curve. So we have initial guesses. I still separated from the previous case. We have you see number of instruments also for this new curve can be different than what we have done for the discount curve. So this can be doesn't need to be consistent, doesn't need to be the same. Those are just different instruments used for calibration. Okay, so we have initial forwards. We have a value of a par swaps. So those are the swap rates seen in the market for this particular, let's say, 3-month LIBOR. And then here we also have maturity. 3-month LIBOR also means that we will need to make sure that the frequency of our LIBORs or our swaps corresponds to 3 months. I haven't, it's actually not really true, so maybe I should not, maybe this 3 month is not a good idea to put it there. Okay, so we define now 3 swaps, and so I call it, 4 swaps. First, we have a discount curve, which is based, this is the yield curve based on this bootstrapped curve here. So this is the first one. And now what we do, we define 4 swaps, where the input is conceptually is a lambda expression of the forward curve. Actually, the curve we don't still have, we haven't found it yet, but we can still define a swap to be a function of it. So you see our swaps, they depend on two additional inputs. So we have a discount curve and also forward curve. Discount curve is given, it's explained here, and those swaps are just lambda expressions of the forward curve that we need still to calculate. But we will actually use the same function as we have done before. So there is no extras that we need to incorporate in our Newton Raphson, Jacobian, everything stays the same. Because here we define that we just need to, we will be searching for a zero coupon bond or yield curve for the forward, and discounting part is handled. So what we do here, we just calculate yield curve. So still our objective here is to match the prices from the, so we have an instrument from the prices from the market versus prices from the model. So here we have those forwards. Those forwards will be used here in the swaps. So we are here in this part, we will be taking those instruments, taking those maturities, R0s and methods. So the method is the interpolation part, and we'll be optimizing to find those values at which swap is equal to 0. So we basically, here, those swaps, we assume that those are par swaps. So then we are only concentrated on the strikes. We are looking for fixed rates, spine points, let's say, for which those swap will be equal to 0 for that particular yield curve. So once this takes place, we can define now, we have initial curve. So this is with R0. So those are the initial spine points. Then we have a forward curve, which are the new, just calculated from this yield curve construction. And then what we do, we will calculate the instruments. So this is what we will double check, or checking whether after the calibration of the curve, we can still price back our instruments. So we will iterate over all the instrument vector we have with all the instruments, and we will calculate we will use this new yield curve as an input to calculate the value of it. Of course, the discounting part is handled, so we will only use the forwarding curve, and then we will plot the values of those swaps. So let's run it. And also there is additional plotting here. So okay, so here we have the first part, spine point. So this is the part corresponding to the discounting. This is also prices for par swap. This is what we have seen before. We needed only seven iterations. And this is the sanity check. So you see that in both cases, swap 1 and swap 2, we got the same value. So implementation of a new swap is consistent. Then we iterate and we try to find out, bootstrap the new curve. Here are the spine points for the new curve. Initial values for our swaps, so you can see that it's really off. And then after the calibration, after bootstrapping, we see that indeed now we're pricing back to par. And here, here this is the plot. So I think the blue line, it's the discount curve, and then we have an orange line, which is the new curve, the forwarding curve. So this is the spread curve. I would say the difference between them illustrates the spread. Of course, here maybe it's not maybe ideal, because what we see is that the forward curve is actually lower. Let me actually we can plot here. We'll do the discount curve. We'll do red, and then for the forecasting we will do blue. Also add legend. Let's see. Yeah, so in this case, actually, we see that the forecasting curve gives us here we are the discount factor. Okay, so that's fine. So we are plotting here only discount factor. So this is just the yield curve. It's not a real yield, but it's only the discount factors. So in order to plot yield, we will need to take a logarithm, as we have done it before, with a minus, and then scale it with time, and then we have a yield. So this is, of course, this you see there is not really, it's maybe smooth, but it's not, it's kind of, it's bending here. This comes from the fact that we have only 4 instruments, so there is no smooth transition between those different maturities. Also, time-wise, it's rather fast. Of course, because we have bootstrapped already our discount curve, so a lot of information already is included in that. So then optimization, you see, is only required 4 iteration compared to the 7 for the discount curve. So this calibration goes relatively fast. Of course, we can extend it, so we can build a new bootstrap curve. We can also bootstrap around this curve. So once we have a discount curve and this new curve, we can create a let's say, third layer. So it's first layer is discount, second layer is the forecasting curve. Let's say for 3 months, we can build up one more curve, which will depend on 2 of them. And that will be actually our homework. Now is the time to summarize what we have learned in this lecture. Of course, this lecture was about yield curves. So as you can imagine, because of the importance of the yield curve, multi-curves, hedging, interpolations, this lecture was longer than typically we have. But I hope that it's a good introduction to, let's say, to the interest rate and also building of yield curves. It is a very important subject. This is also the reason why I decided to spend significantly more time on the subjects covered in today's lecture. First, we started today, this lecture started with a yield curve and its dynamics. So we explained what is the yield curve, how it actually, how to interpret different shapes of the yield curve, and what are the let's say, what is behind the dynamics of a curve. Then we went for the mathematical formulation. So from economical perspective, it was clear how the curve behaves, what are the different phases of a yield curve. And then we defined mathematically the problem of a curve, because that was necessary to build the curve using a numerical implementation. So we need to know mathematically what's the problem, how we can formulate the problem of a yield curve building or yield curve calibration. Next step was to relate construction of a yield curve with a search of implied volatilities that we have already discussed in the computational finance course. So this was maybe a little bit of a refresher. Then the subject that we covered was spine points and optimization routine. So what is the impact of the different optimization routines and how this is related to the calculations of spine points. Something new, of course, was analytical example of a yield curve. I always find this example quite funny, because normally we just handle everything in computer, but here step by step we illustrated how this would work if you have a simple simple example how to do it yourself on a piece of paper if you wish. Then, of course, the Python experiment, when we went through the codes, and I explain you what are the main important elements of this code, how possibly you can extend it. Also, we also extended this code once we talk about multicurves, of course. Next task was to talk about to develop the framework for hedging. What is the impact of different interpolations? So that was kind of important subject, not only from a theoretical perspective, but very practical. And then we went to the last block about multicurves. I gave you motivation why the curves are important, multicurves are important, how to connect the multicurves to probabilities of default, what is the relation between discounting and also forecasting. And we went also through the Python code on how to implement that, how to extend the existing framework to handle multicurves. And now is the time to summarize, of course, and give you homework. Homework is very much based on implementation. So we have two tasks. The first task is to extend the existing code for building of a curve and introduce additional instruments. So in the code that I have presented, we focused only on swaps. Your task will be to also include fraz and floating grid nodes. And the second part is also coding, is to extend the framework with additional layer of a forward curve. So right now we have only it's called base curve, or we have discount curve. We also have a 3-month, let's say, forecasting curve. Your task is to include additional layer where you have a new curve, which will depend on both 6 months, 3 months, and also the instruments, let's say, quotes in the market. Keep in mind that the codes that I have provided you, we everywhere relied on the fact that the market quotes are quotes par quotes. So the value of a swap is given equal to 0. This is why it's slightly maybe different what we have presented in the slides where you had these QIs. But I also mentioned that typically price of a swap that is used to build a curve is at par, so it means its value is 0. I hope this lecture was insightful and you have learned a lot. And of course, I would like to invite you to the next lecture where we will further expand our knowledge on pricing of swaptions. So we use building of curves, etc., into more application, and also we will link that to volatilities, implied volatilities in the interest rate world. See you next time.